Hello, good afternoon. So today we are going to see the binary search tree, which is a type of binary tree. So we are in the second unit of data structures and algorithms, and that is trees, right? So we are going to see what is a binary search tree today. So let us go ahead and see what are the contents of the today's lecture. So today we have these contents. So we are going to see, or we are going to learn what is a binary tree, how we can convert a general tree where each node can have any number of nodes. There are no limitations of the number of subtrees or number of children a node can have. So how to convert that general tree to a binary tree? So that we will see. We will also see what are the different types of binary trees, and after that we will see what is a binary search tree and what are its different traversals. So traversal is nothing but like visiting each element of the tree, visiting each node of the tree in a specific order, visiting each node of the tree in specific order. So these orders are, or these orders can be pre-order, in order, post order, BFS, that is breadth first search, and DFS, that is depth first search. So let us go ahead and start with what is a binary tree first. So here, these are the properties of a binary tree, where the first property is, in binary tree, any node can have either 0 or 1 or 2 children, right? So if it is a leaf node, it will have 0 children. And if it is a internal node, it will have either 1 or 2 children. So not more than 2. So that is binary tree. And there is one more property, that maximum number of nodes at any level, like in the trees we have level 0, level 1, level 2, and so on, where root is at level 0, right? And then its children are at level 1, and then its grandchildren are at level 2, right? So at any level, the maximum number of nodes in a binary tree will be 2 raised to L minus 1, where L is a level of the node, where L is level of the nodes, right? So here there is a consideration for this formula to become true, and that consideration is, consider the root is at level 1. Consider the root node is at level 1. So like we are starting with level 1, then level 2, and then level 3, and so on, right? So consider root is at level 1. So that is level 1. So how many nodes are maximum on level 1? Only 1, right? So is this formula working here? So see, 2 raised to L minus 1. So it is 2 raised to 1 minus 1, and that is 2 raised to 0. And 2 raised to 0 is 1, right? So maximum number of nodes on level 1, that is root, is 1. Now on the next level of the root, that is the children of the root. So how many children of the root are possible? Only 2, right? Maximum 2. So what is the level? Is 2, right? So it is 2 raised to 2 minus 1. So 2 raised to 2 minus 1 is 2 raised to 1, and 2 raised to 1 is 2, right? So this is how this formula works if we consider the root is at level 1. Now after level 2, there is level 3. So on level 3, there are maximum 4 nodes possible, right? From the 2 parent nodes of level 2. So level is 3. So 2 raised to 3 minus 1. 2 raised to 3 minus 1 is 2 raised to 2, and 2 raised to 2 is 4, right? So this is how this property works for binary trees. Now third property is maximum number of nodes. Maximum number of nodes in the tree. So if we have a height of the tree, or we know the height of the tree, then we can find out maximum number of nodes using this formula, 2 raised to h minus 1. 2 raised to h minus 1, where h is the height of the tree. But for that, we have to consider the root is at level 1, right? So consider there is only root. So 2 raised to 1 is what? 2, and 2 minus 1 is 1, right? Now consider there is root and then its children. So it is 1 plus 2, maximum 2 children, right? So 1 plus 2 is 3. So height of the tree is what? 2. So 2 raised to 2 is 4. 4 minus 1 is 3, right? Now consider we have a root, its children and grandchildren. So it's 1 plus 2, 2 plus 4, and that is, it's 1 plus 2, 3, 3 plus 4, 7, right? And height of the tree is 1, 2, 3. So it is 1, 2, and 3, right? So 2 raised to 3 is 8, right? And 8 minus 1 is 7. Okay, so this is how we can find out maximum number of nodes in the binary tree using this formula if we know the height of the tree where root is considered as at level 1, and that is 2 raised to h minus 1. Okay, so these are the some properties which are true for binary tree. So let us go ahead and see an example of binary tree. So here you can see we have a root node that is 2, then its left child is 4 and right child is 10. So here in the binary tree we can use these terms left child and right child. Why? Because here maximum number of children are 2. Maximum number of children are 2. So they can be either left child or right child, right? So 2's left child is 4 and 2's right child is 10. Now 4 has a left child that is 6 and right child is 5. Now 2 has a right child 10 and 10 has a right child 11, right? So this is how it works. This is how it works, right? So this is a binary tree. Now you can see like 2 has 2 children, 4 has 2 children, 10 has 1 child, and now 6, 5, and 11 has 0 children. So all the nodes are having what? Either 0 or 1 or 2 children, right? So this is what? Binary tree, right? Now we'll see how we can display this binary tree. So if we take first, that is pre-order. So what is pre-order? पहले आप data को visit करेंगे and then you will search into left subtree and then right subtree. So first visit data and you will apply this formula on each node. So that is why if you see here, we start from root, right? So 2 is the root and now we have pre-order. So pre-order is what? Data, left, right. So what is the data? 2 is the data, right? Now from 2 we'll go initially we visit 2 and then we'll go to left. So on left there is 4. So on 4 also we have data, left, right. So visit data 4 and then go to the left. So for 2 and 4 its right is remaining. Okay, so we are going to left and that is 6. So on 6 again data, left, right. So visit 6, then checks left, that is null, then check right, that is also null. So go back. Now 4's data and left is over, right? Data and left is over. So its right is remaining. So from 4 go to right and that is 5. So on 5 data, left, right. So visit 5, then check left, that is null, then check right, that is null. So go back. Now 4's data, left, right is over. So go back. Now 2's right is remaining. So go to 2's right and then visit data, check left. So data is 10, left is null. So go to right. Now on 11, data, left, right. So visit data 11, then check left and then check right. Okay, so this is how we have visited in pre-order, that is 2, 4, 6, then 5, then 10, then 11. So this is what you can see is pre-order 2, 4, 6, 5, 10, 11. Now what is in order? What is in order? So in order में क्या है? जैसे in pre-order data was first. Similarly, in order data will come in between left and right. So LDR, left, data, right. Okay, so you start from root, that is 2. So on root, left, data, right. So first go to the left, do not visit 2, do not access 2. Okay, just go to first left. On 4 again, left, data, right. Go to 4, left, that is 6, and then visit left. So left is null, then visit 6. So until you do not get left null, do not access the data, right? So 6 का left आपको दिखेगा, 6 has left null, then visit what 6 and then check right. So left data right, but right of 6 is also null. So go back for 4 and 4's left is over. Now visit data, that is visit 4 and then go to right. So 4's right is 5. Again check initially left, left is null, then visit data 5 and then check right, right is also null. So go back. Now 4's left data right is over, so go back. Now 2's left was over, so visit data 2 and then go to right. So left data right. On 10 check left, it is null, then visit 10 data and then go to right. On 11 you can see, first go to left, left is null, then visit 11 and then go to right, right? So this is how, what is the in order? It is initially 6, then 4, then 5, then 2, then 10, and then 11, right? So this is in order, right? In order traversal, 6, 4, 5, 2, 10, 11. Now what is post order? So post order is what? First left subtree, then right, then data. So you start from 2 and then from 2 you will go to left, from 4 you will go to left, then from 6, from 6, from 6 you will check, you will not visit the data, right? You will go to left, that is null, then you will go to the right, then that is also null, then visit data and that is 6. Okay, so left and right is null, then you go for, you first check left, then check right and then data, that is 6, right? So left, right and then data. So initially you visit 6, then go back. So 4's left is over, then check right and that is what 5. So check 5's left, right, that is null, so visit 5. So left, right and then data. So initially you visited 6, then 5, then go back. Now 4's left and right is over, so visit 4 now, then go back and then it's 2, right? So 2's left is over, so do not access 2, go to its right. Then on 10 left is null, then right, go to right of 10 and that is 11. Now left is null, right is null, then visit 11. Now 10's left, right over, so visit 10, go back and then 2's left and right is over, then visit 2. So what is the post order? Post order is 6, 5, 4, 11, 10 and 2, right? So this is the post order, right? This is what you can see is post order traversal, that is left, right, data 6, 5, 4, 11, 10 and then 2, right? So आप देख सकते हैं यहाँ पे in the pre-order root is 2, right? And then after 2 the nodes in the left subtree, that is 4, 6, 5 and then nodes in the right subtree, that is 10 and 11. Okay, in order you can see initially there is a nodes in the left subtree, then there is root and then the nodes in the right subtree. So left, data, right. And in the post order you can see initially 6, 5, 4 are the nodes in the left subtree, then 11, 10 are the nodes in right subtree, and then root node, that is 2. So left, right and then data. So this is how root comes first in pre-order. Root comes in between the left and right subtree nodes in order, and in post order the root comes after the nodes of left subtrees and right subtrees. Okay, then there is a breadth first search where you visit the nodes level wise, like level 0 has 2, level 1 has 4 and 10, level 2 has 6, 5 and 11. So the breadth first search is 2, 4, 10, 6, 5 and then 11, right? So this is level wise and that is called as breadth first search. And after that there is a depth first search. So what is the depth first search? You start from 2 and then you go to bottom. So 2, 4, 6, then come back and go to bottom again, that is 5. then come back and then go to the bottom again, that is 10 and 11. So you start from top, reach to the bottom, like 2, 4, 6, go back, then 5, go back, then 10, then 11, right? So this is how depth first search is, right? So you can see here, this all traversals, pre-order, in order, and post order, and BFS and DFS. So you can see here, this DFS is similar to pre-order. Why? Because in pre-order also we visit the data and then we go to left. So that is, we are going from top to bottom. So pre-order and depth first search are actually the different algorithms, but their outputs are same. Now we will see the types of binary trees. And here we have a full binary tree, complete, perfect, balanced, and degenerate. So what is full? So in full binary tree, all the nodes will have exactly 0 or 2 children. So there will not be a node having single child. So each node will have either 0 children, so it is a leaf node, or if it is an internal node, it must have exactly 2 children. An example is this. You can see the first tree, and that is full. So you can see the root is having 2 children. Then first child of the root has again 2 children. Then its grandchild also has 2 children. So all the nodes are having 2 children except leaf nodes, and leaf nodes are having 0 children. So all the nodes are having exactly 0 or 2 children, and that is full binary tree. Now you can see here complete binary tree. So what is complete binary tree? Where all levels of the tree are full. That is, all the nodes will have exactly 2 children except the last level. So you can see here the complete binary tree. So here level 0 is full, level 1 is full, level 2 is having 1 node less, right? So that is last level is not full, and that is what complete binary tree, where all the levels are full except last. Now next is perfect binary tree. So in perfect binary tree, all the internal nodes have exactly 2 children. So internal nodes जितने भी रहेंगे except leaf nodes, उनको कितने children रहेंगे? Exactly 2. So this is the example of perfect binary tree. You can see here, it is like first node has 2 children, exactly 2, and its children also has exactly 2 children, right? So grandchildren are 4. So this is a perfect binary tree. And after that, we have a balanced binary tree. So here in balanced binary tree, the root node has 2 subtrees, like left subtree and right subtree. So their height will have either the same height, or their height will not be vary by more than 1. For example, the height of the left subtree can be 2, right subtree can be 2, or it can be 2, 1, 1, 2. So difference should not be more than 1. So you can see here in the example, there is a root and left subtree having height 0, 1, 2, and right subtree has a height 0, 1. So it's 2 and 1. So difference is not more than 1, and that is why this binary tree is balanced. And last type is degenerate. So balanced binary tree has 2 examples, and that is AVL trees and red-black trees. So AVL trees and red-black trees are balanced binary trees. And what is a degenerate binary tree? That is, every internal node has only a single child. So आप देख सकते हैं, what is degenerate? Each node will have a single child. So यहाँ पे किसी भी मतलब नोड को 2 चिल्ड्रन नहीं रहेंगे, 2 ब्रांचेस नहीं रहेंगे. तो इसका मतलब क्या है? It will go in a single direction. It will not go in 2 directions, right? So it will having a linear structure like a linked list, right? So these are the types of binary trees, and how to convert a general tree into a binary tree. So आप देख सकते हैं यहाँ पे A has 6 children, B, C, D, E, F, G. Now B has 3 children, H, I, J. E has 2 children, K, L. G has a single child, M. Then H has N, O. K has P, L has Q, and so on, right? So here, how to convert this general tree into a binary tree? So start with root. So binary tree means a node cannot have more than 2 children, right? So start with root A. Now what after root A? A has 6 children, B, C, D, E, F, G. So make the first child as the left child of A. Okay, out of 6 children, the first child of A is B, and make that first child the left child of A. That is, A's left child is B. And all the other children of A will be connected in the right subtree of A's left child. That is, C, D, E, F, G are connected into the right subtree of B. So you can see B के बाद right subtree है उसका C, D, E, F, G. Now again for B, in general tree you can see B has 3 children, H, I, J. So the first child of B become its left child in the binary tree. So B has a left child H, and other children of B, that is I and J, will be connected into the right subtree of H. Right subtree of H. Similarly, H has 2 children N and O. So N becomes the left child of H, and the second child of H will become the right child of its first child, that is N. Okay. Similarly for E, E has 2 children K and L. So the first child will become the E's left child in the binary tree, and second child of E will be connected into the right subtree of K. Right. So this is how we can convert a general tree into a binary tree. Like G has a single child M, so it becomes left child of G, and that is M. K has a single child P, it will become left child of K. L has a single child in general tree, that is Q, it will become left child of L in binary, right? So this is how we can convert a general tree into a binary tree. So we have seen now a lot of things about binary trees. Now we'll see what is a binary search, right? So binary search tree is what? Where a node will have, like, we start from root, right? Now this is also a binary tree, so a node will have either 0, 1 or 2 children, maximum 2. So if we start with a root and then we have a left child and right child, so you can see the left child will be always smaller than its parent, and the right child will have a value or data which is greater than its parent. So that is only the rule of binary search tree, that basically it is a binary tree. And second is each parent node, okay, including root node, will have the left child which is smaller than parent or root, and right child has a greater value than root. So that is what binary search tree. So this formula is applicable for each level, for each node. Like you can see 11 has 7 as a left child, which is smaller than 11, and 12 as a right child, which is greater than 11. Now 7 has 5 as a left child and 9 as a right child. So 5 is smaller than 7 and 9 is greater than 7, right? Similarly, हम देख सकते हैं दूसरे examples. Now these are the traversals of this tree: pre-order, in-order, post-order. Okay, so what is pre-order for this tree? पहले data, then left, then right. So pre-order is 11, 7, 5. Okay, so 11, then left, 7, then left, 5, then left, then right, then go back, then it's 9, then 8, then 10, then 12, 4, and 13. So it's pre-order. What is in order? Left, left, left from 11, right? So 5, then 7, then 8, then 9, then 10, then 11, then 4, 12, and 13. What is post order? Left, right data. So it's 5, then 8, then 10, then 9, then 7, then 4, 13, 12, and then 11. It is post order. What is BFS? 11 level wise, bread for search, BFS, right? So it's 11, 7, 12, 5, 9, 4, 13, 8, and 10, right? So these are the BFS. And what is the DFS? Depth first search, 11, 7, 5, then 9, 8, 10, 12, 4, and 13, right? So these are the traversals of above tree. And after that, we have this one more tree, and that is a again binary search, right? So यहाँ पे देख सकते हैं आप, you can see here there is a root 21. Now 14 is a left child, smaller than 21. 28 is a right child, greater than 21, right? So 28 is greater than 21, right? Similarly, 14 has 11, smaller value, as a left child, and 18, which is a greater value, as a right child. Now 11 has left child 5, smaller, and right child 12, greater. 18 has smaller left child 15 and greater right child 19, right? 25 has smaller value as a left child 23 and greater value as 27, which is a right child. Now 32 has left child 30 and right child 37. So this is how this works. Now in this tree, if I want to search 27, so how I will search? Initially I will compare 27, okay, जो मुझे search करना है. So to search 27, I will compare initially it with root. So 27 is not matching with the root. So check whether it is smaller or greater. So it is greater than 21. So go to right. So in right, we get 28. So compare 27 with 28. It is not matching, but it is less than 28. So go to the left side. Then on 25, it is not matching with 27, but it is greater than 25. So go to the right, and then on 25's right, we will get what? 27. So as it is a binary search tree, we can apply this, whether a key is matching with the node or whether it is smaller or greater, and then we can take or we can move either left or right. So actually that reduces the number of comparisons. Like to search 27 in a binary search tree, how many comparisons are required? 1, 2, 3, and 4, right? 21, 28, 25, and then 27, right? So अगर ये binary search tree नहीं होता, that means if it would not be a binary search tree, if it is a binary search tree, so how many comparisons would have required to search 27? Definitely more than 4, right? Because we have to search from root, then nodes in the left subtree, then nodes in the right subtree, and so on. So it would have taken how many comparisons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 comparisons, right? But because of binary search tree, we found 27 in only 4 comparisons, right? So here there is only like if you want to find root, that is 21. If your key is root 21, you will find it in single comparison. If your key is the nodes at level 1, so you will need 2 comparisons. If your key is from level 2, so you will need 3 comparisons. And if your key is from level 3, you will need 4 comparisons. So in binary search tree, if the node to be searched is at level L, so the number of comparisons required to search that node are L plus 1. Okay, so this is how binary search tree is search efficient. It simplifies the searching operation and reduces the number of comparisons, right? And these are the traversals of binary search tree, which is given above. And thank you. So I hope you have understood what is a binary tree, what are the types of binary trees, how we can convert a general tree into a binary tree, then what is a binary search tree, and how binary search tree simplifies the searching operation, how it actually reduces the number of comparisons required to search an element or a key value. So thank you. I hope you have enjoyed the content. Have a nice day. Thank you.